Driving is a continuous negotiation with chaos. A sudden downpour, a slick road, a person stepping off the curb without warning. Every second throws a new, unique scenario at a vehicle. For decades, software engineering relied on rigid logic. If a system received input A, it had to output an exact, predetermined answer B. You could test it, grade it, and know with certainty if it worked. But an autonomous vehicle's brain relies on artificial intelligence to process noisy, unstructured data, like video feeds and LiDAR point clouds, constantly estimating the likelihood of what it sees. This creates friction. Engineers are trained to look for exact mathematical truths, but they are now tasked with evaluating a system that communicates in probabilities. Traditional validation methods break down here. It is impossible to evaluate a probabilistic model using a simple true or false rubric. This friction leads to the oracle problem. When we evaluate an AI's decision on a complex scene, there is often no definitive correct answer key to check it against. Look at this diagram. We have a pedestrian partially hidden by dense fog and camera glare. The AI draws a bounding box to detect them, but the image is so degraded that a dozen slightly different boxes could all be technically acceptable. Now, scale that single ambiguous moment up to the entire world. A vehicle faces infinite combinations of lighting, weather, and human behavior, a challenge known as the Curse of Dimensionality. Even with massive simulation banks, attempting to brute force test every single one of those combinations is physically and mathematically impossible. To build a case for safety, engineers have to move beyond the search for perfect answers and find a way to measure reliability within an infinite environment. One solution is a technique called metamorphic testing. It allows us to evaluate AI even when we don't have a specific target score. Instead of grading a single output, we validate the logical relationship between two different executions. In a baseline scenario, the vision system detects a pedestrian on the right with high confidence. If we horizontally flip the scene and add severe rain noise, the detection box must accurately mirror to the left, maintaining a stable confidence score. By proving the AI's logic holds together when the input is manipulated, we can verify its internal reasoning even without a numerical answer key. Validating logic solves one problem, but we must apply these tests across endless variations of the real world. Rather than endlessly testing random scenarios, safety engineers use combinatorial testing to focus on the most high-risk variables. This relies on the statistical observation that systems rarely fail because of one factor. They fail when specific, difficult conditions overlap. This matrix isolates three axes: nighttime, heavy fog, and dark clothing. Testing every mundane variation takes lifetimes. Instead, the matrix collapses to the exact intersection of these extreme variables, creating a highly efficient, targeted test suite. This optimization allows teams to cover a vast operational domain by focusing on the boundaries where the AI is most likely to be stressed. These methods represent a shift in how we approach the unknown. By moving away from the impossible task of testing every mile, we can begin to define clear boundaries for AI behavior. Metamorphic testing ensures logical consistency, while combinatorial testing targets the compounding variables that lead to real-world failures. This structured approach helps quantify the residual risks that are inherent in any probabilistic system. It provides a framework to identify failure points that would be nearly impossible to find through random testing alone. By mastering these principles, engineers can build a rigorous safety case, reducing the uncertainty of the road to a level that we can measure, manage, and eventually trust.